Hey man, let's get stuck into this. We'll start with converting radicals, which are expressions with a root sign like that, and fractional indices. You use this rule here. It says if you have something to the power of a fraction, the numerator, the number on top of the fraction, becomes the power, and the number on the bottom of the fraction tells you which root it is. So if you have something like this and you want to convert to a fractional index, so we'll leave the same base as x. The power 8 goes on top, and which root it is, 5, goes on the bottom. For this one here, because we have this negative power, first thing we're going to do is move it to the bottom of the fraction and change its power to positive. So I'm now going to convert this here to a radical, so with the root sign. So the number on the bottom, 7, tells you which root it is, and the top number tells you the power. And we still have our 1 on the top. Now, if you have to perform operations with radicals like this, first convert them to fractional indices. So let's convert that to a fractional index. So that will be x to the power of 5 over 4. Square root of x is the same as x to the power of a half. Square root is the second root. And on the bottom, power goes on top of the fraction, and which root it is goes on the bottom. Now we can use our normal index laws to perform multiplication. We keep the same base and we add the powers. So now we're going to divide. That's what the fraction line means. So we keep the same base and we're going to subtract the powers. And we get x to the power of 11 over 8. So if you're asked to write this as a fractional index, which number's on the bottom, the denominator, that tells you the root, and the top number tells you the power. How easy is that? Let's look at some modeling. So for exponential modeling, we use the equation y equals ab to the power of x. So just be careful here. Because of order of operations, this is done first, so only the b is being raised to the power of x. So a is the initial or starting amount, and b is the rate. It's usually a percentage, so we write as 1 plus whatever the rate is divided by 100. So this is very similar to the worded problems you would have done with geometric sequences. This is very similar to a r to the power of n minus 1. In fact, you could use that formula as well, but I'll use this exponential modeling formula. So let's look at the question. Population of a town decreasing by the same percentage each year. That means that this is exponential. It means that it's decreasing at a decreasing rate. It's not linear. What that means is population is projected to be 7,763 in 6 years, and this in 12 years. So the population's gone down from here to here by about 230 people, but it's not linear. It doesn't mean that the population is going down by 230 every single year. Because it's decreasing by the same percentage, it's exponential. So what will actually happen is in the next 6 years, it would decrease by fewer than 230 people. So we need to use this formula here. So after how many years will the population have halved? You have to ask yourself, okay, well, what do I need to know in order that I can answer that? Now, we won't be able to answer this without knowing A and B. So we have to find A and B, and anytime you have to find two quantities at once, think simultaneous equations. So what I'm going to do is take this information and substitute it. So this will be y and this will be x. And similarly, my second equation, because you need a second equation for simultaneous equations, it will be yx. So here we have two equations and two variables. Now we want to eliminate one of them. We can't do that by subtracting. Subtracting, say this from this, won't get rid of either A or B, but we can get rid of them by dividing. Now when we're dividing equations like this, always do the larger power divide the smaller power. It's just easier that way. So when I divide A by A, they'll cancel out, and B to the power of 12 divide B to the power of 6. We kept the same base and subtracted the powers. So now I'm going to do this number divide this number. So putting this on our calculator, we get about 0.9703, and it keeps going. Now I'm just going to write a few digits to save time, but in my calculator, I need to use this exact value. My next step to get b by itself is to take the 6th root of that. So I'm going to take 6th root of a and s answer in my calculator. So when we do that, we get an answer that is close enough to 0.995. So 0.995 is 1 minus 0.05 over 100. That's B. That means the population is decreasing by 0.05% each year. All right, let's now find A. Finding A won't be too difficult. We just substitute that into either of these equations. I'll just choose this one. So I have this equation here after substituting B for 0.995 here. So of course, this is just a number. It's not a nice number, but it's a number nonetheless. The way we undo timesing by a number is dividing by a number. So I just go 7763 divided by this number here, and I get that A is close enough to 8,000. So that was the initial population of the town. It was 8,000 decreasing by 0.05% per year. Okay, so after how many years will the population have halved? Well, let's go back up to this equation here. I know that I have y equals A times B, 0.995 to the power of x. Now, if the population's halved, that means it's now going to be 4,000. So I substitute y for 4,000. Now, when you're here, remember what I said before? We don't times these together, because order of operations means this is done first. What I'm going to do is divide each side by 8,000, and I get this exponential equation here. Now, when you're finding an unknown exponent, something unknown in the power, you use logs. So when we're using logs, this thing that's being raised to the power, that is the base, and the other number is our power. You can put it straight into your calculator like this. I think it's math and option A for log base. And we get about 138.28. So that means after 138 years, we're just short of halving it. It'll be a little more than half. So we just round these up. So it will halve in about 139 years. All right, let's now have a look at some exponential equations involving quadratics. So this equation here may not look like a quadratic, but it actually is. The reason is 16 to the power of x is just 4 squared to the power of x. But our index laws tell us we multiply these two together. So it doesn't matter the order in which you multiply them. So I could just as easily write it as 4x squared. So when you have something and something squared, you should think quadratics. Now, because it's not written the way that we're used to solving quadratics, it might be easiest for us to make this substitution y equals 4 to the power of x. So then this thing here, that becomes y squared. Now notice that 4 to the power of x plus 1 is the same as 4 to the power of 1 times 4 to the power of x, because we keep the same base and add the powers. So this is 4y. So we have y squared minus 4y equals 32. Now whenever we're solving quadratics, we make one side equal to 0. So when you're here, you can probably just put it in the polynomial solver of your graphics calculator, or we can factorize it like this. So we end up getting y equals 8 or negative 4, but we're not done here. We weren't asked to find y, we're asked to find x. So I'm just going to replace y now with 4 to the power of x. So I have 4 to the power of x equals 8 or negative 4. So now I'm going to solve each of these individually. So if 4 to the power of x equals 8, you may be able to see the solution. If you can't, x will just be log. Now here 4 is the base, so it goes down here, log 4 of 8, which is 1.5. So the other option is that 4 to the power of x equals negative 4. This actually has no solutions. If you raise 4 to any power, you will always get a positive number. So we can disregard this as it gives no solutions. That's the reasons why you can't have log of a negative number like log of negative 1 or whatever. Because if you raise a positive number to a power, the answer has to be positive. It can never be negative. So this is our only solution, and we're done. All right, best of luck studying, but you'll ace it. You're a superstar. I'm proud of you. Look forward to seeing you do great things.